Thank you very much. I'm really delighted to be here and to present this talk, which is a part of a joint work with Maria Emilia Maietti from the University of Padova. And well, as you can expect from this kind of title, the main purpose of this talk is to explain and to revisit the notion of Presheaves, sheaves, and sheafification, which are well known and used in algebraic geometry, categorical logic, and category theory, through the notion of triposes, which are a particular kind of Lovira hyperdoctrines. So this is the main purpose and the main topic of this talk. And before starting with all the detail, I would like to quickly start with a little bit of summary behind the notion of tripos and of tripos-to-topos construction. So, in categorical logic, there are two well-known families of toposes which are well-known and used. The first one is the family of localic toposes. These are toposes built from a given locale. So we have a locale which is essentially a generalization of a topological space, and we can construct the topos of sheaves over this locale. And on the other hand, we have a family of toposes which are realizability toposes, which are essentially a categorification used for realizability models. In this case, we have a topos which is constructed starting from a PCA, which is a partial combinatory algebra, which is a generalization of Pliny's first model. A relevant example is, of course, Martin Hyland's effective topos. And well, we have these two well-known families. And while it is well known, of course, that localic toposes are a crucial example of Protonic toposes, realizability toposes are just elementary toposes in general. So this is a big difference between these two families. And the second one is that localic toposes are not in general an instance of the exact completion of a category with finite limits, while realizability toposes have been proved to be an instance of the exact completion of the category of partition assemblies. So we have these two families. And essentially, Hyland, Johnstone, and Pitts introduced the notion of tripos and the notion of tripos-to-topos for essentially they wanted to understand if these two different categories, from an abstract point of view, are, for example, instances of the same construction, even if they are so different as we have seen. And in this paper, in tripos theory by Hyland, Johnstone, and Pitts, they introduced the crucial idea. So the crucial idea is that the ordinary category of sheaves on a locale can be described in terms of A-valued sets, essentially. This is a construction this is a result due to X or Fuhrman and Scott. So there is an explicit way for describing the category of sheaves on a locale. And this description can be generalized to a particular kind of functors which are called triposes. And as I said, this is another piece of the abstract of the second work by Pitts, tripos theory in retrospect. The notion of tripos was motivated by the desire to explain in what sense X description of sheaf toposes as age-valid sets and Hyland realizability toposes are instances of the same construction. So, they introduced this notion of tripos, that is a particular kind of Lovira hyperdoctrine. We will see all the detail later, but I want at least to give you an idea before starting with all the detail. So it is a functor from the opposite of the category of sets into the category of Heyting algebras, and the idea is that this functor, it has a null structure to properly deal with higher order logic. Here there is a quick explanation for the name, and well, they introduce a generalization of the notion of category of age-valued sets, and they call this construction the tripos-to-topos. So the idea is that we can start with a tripos, and we can apply this construction, obtain it, and we obtain a topos, denoted in this way. And this this result is contained in these two works, and this is a generalization of the construction of the category of sheaves on a locale. So if we have a locale, we can take a special tripos, applying this construction, and obtaining the category of sheaves over this locale. So this is the setting. If we have a localic tripos, if we have a locale, we can define a tripos called localic tripos. And if we have a PCA, we can define a particular functor that is called realizability tripos. And if we apply the tripos-to-topos construction to these two functors, we obtain here the topos of sheaves on a locale, and here the realizability topos associated with this PCA. So from an abstract point of view, these two families of triposes can be obtained as instances of the same construction, of course starting from different triposes. So this is the original work and motivation by Martin, Hyland, Pitts, and Johnstone. Our main contribution is essentially the following. We want to recover the geometric meaning behind such a construction, because it is well known that, for example, the notion of sheaves can be presented as a particular Presheaves with respect to satisfying certain condition, right, and with respect to topology. So we have that, for example, in the localic case, we can construct also the category of Presheaves over the locale, and there is an adjunction, which is the Sheafification, between this category and the category of Presheaves. So this is well known in category theory and algebraic geometry. What we want to prove is that we can generalize all this situation for arbitrary triposes. So for any tripos, we can define a category generalizing the category of Presheaves for a locale, and we can define a new functor here, a new tripos, which is obtained essentially by freely adding new existential quantifier. There is an adjunction here, and when we apply the tripos-to-topos to this functor, we obtain precisely the abstract topos of Presheaves, and when we apply the tripos-to-topos construction to this adjunction, we obtain precisely an adjunction generalizing the ordinary sheafification. So in this sense, we want to be able to present the notion of tripos-to-topos in terms of Liouville-Tierney topologies for a certain category of abstract Presheaves. This is the idea, and this is the main result that I'm going to present today. Now, in our work, I want just to quickly explain that we worked in a more general context, so for arbitrary-based triposes, but in this case, moving in this more general context, well, there are some differences. In particular, the main difference is that we can reproduce the old picture that we saw in the previous slide, but the difference is that the category of Presheaves associated with a tripos over an arbitrary base, it is just an exact category, and the existential completion of this tripos is not a tripos, but it is just an elementary in the existential doctrine. And well, in our work, we also provide a characterization of those triposes such that this category is precisely an elementary topos and this is a tripos, and we call them existential triposes essentially. So this is our main result, and today I'm going to present all the detail of the previous picture for set-based triposes, which are those originally introduced by Hyland, Johnstone, and Pitts. So what a tripos is? A tripos, as I said, is a functor from the opposite of the category of sets into the category of aping algebras, such that for every function, the reducing functor, I'm denoting in this way the functor obtained by applying the functor P to this function. It has a left adjoint and a right adjoint, and this is satisfying the Back-Chevalier condition, which basically means that the quantifiers commute properly with the substitution. And then, and this is the crucial point, there exists a generic predicate that is a set and an element of this set, such that for every element alpha of this fiber, there exists a function such that alpha is equal to this element. So this is where this condition basically it means that this functor, this tripos, it is strong enough to properly deal with higher order logic. An example, if we have a locale, we can consider the representable functor assigned to a given set deposit of functions from this set to the locale with the pointwise order, and this is a tripos. And here, there is a second example of the realizability tripos. So in this case, we have a PCA. I don't want to give all the detail because it is quite technical, but I want at least to give you an idea. But so, for every set, we can define a partial order in this way, where the elements again are functions from the set X into the power set of the PCA. And we say that two elements, we say that alpha is less or equal to beta if there exists an element of the PCA such that for all the element X of the set and all the element of this set, this application is defined and it is still an element of this set. This just for quickly explain that we can define, starting from a PCA, another tripos, which is the base for the construction of the realizability topos. Now, the tripos-to-topos construction. Here I quickly summarize all the detail of the tripos-to-topos construction, and here you can find all the references. I don't want to give all the detail here, but I want at least just to give you an idea behind such a model. If we have a tripos, we can define a topos, whose objects are essentially pairs where this is a set, and this is essentially a relation satisfying these two conditions, that is the symmetry and the transitivity. And essentially, a morphism from an object of this kind into an object of this kind is essentially a relation which is functional and total with respect to these two relations here. So this is the idea. We are using the logic inside tripos to define a category, because this can be seen as formulas, for example, and this construction provides a topos. Examples, as I said before, if we start with a locale, and we consider the localic tripos, we have that if we apply tripos-to-topos construction to this locale, we obtain, to this localic tripos, we obtain precisely the topos of localic sheaves. And the same for the PCA and the realizability tripos. We can apply the tripos-to-topos construction to the realizability tripos, obtaining an equivalence between, essentially the tripos-to-topos provides exactly the realizability topos associated with this PCA. So this is the setting. And these are all results due to Martin, Hyland, Johnstone and Pitts in these two papers. Now, we want to define a generalization of the Presheaves construction in this context of triposes. So, we can consider a tripos, and we define the category of P Presheaves in this way. First, let us consider the Grothendieck category associated with this factor, or category of points. This is the category whose objects are pairs, where the first element is a set, and the second one is an element of this fiber, and whose morphisms are functions from A to B, such that the first element is less or equal to this second element, where we are applying this reindexing to the element beta. And now, given this category that is called Grothendieck category of points, we can define the category of P Presheaves as the exact completion of this category, which is a category with finite limits, so it is a Lex category. So we can define the category of P Presheaves in this way. The first result is that for any set-based tripos, this category is an elementary topos. Example, In the case of the localic tripos, if we apply our construction, we obtain precisely the category of Presheaves on this locale. Essentially because the growth and deconstruction associated with this functor is exactly the same of the coproduct completion of the locale. And it is known due to, for example, this is a result observed by Carboni, for example, that the exact completion of this category is precisely the category of Presheaves. While in the case of the PCA, we obtain a new category. The Presheaves category is a new category which really looks like the exact completion of the category of assemblies, but it is a little bit different. Now we want to show that also this construction, so the Presheaves construction, can be presented via the tripos-to-topos construction, but we have to introduce a second crucial completion that we have to apply, that is the existential completion. Now, what is the existential completion? If we have a functor, more generally a primary doctrine, so an arbitrary functor into the category of things similarities, we can construct a new doctrine which is existential, which means that it has left adjoints along all the radiusing, and we denoted this doctrine this way, and this is called the exact completion of the doctrine P. We first proved that for any tripos, the existential completion of this tripos is again a tripos, and then that the tripos-to-topos construction applied to this functor is precisely the category of Presheaves for this functor. So, the Presheaves, the construction of the category of P Presheaves can be obtained by first applying to this functor the existential completion and then the tripos-to-topos. Then, we proved that for any set-based tripos, there is an adjunction between this tripos and its existential completion. And, when we apply the tripos-to-topos to this adjunction, we obtain an adjunction between the category of Presheaves and the category obtained in the tripos-to-topos category, which abstract precisely the ordinary sheafification. So, for any, as a corollary, we have that for any tripos there exists a Lovir-Kearney topology denoted in this way on this category, such that the tripos-to-topos construction can be presented as the category of sheaves with respect to this topology for this category of Presheaves associated with this doctrine, with this tripos P. And this is our main result, because in this way we are obtaining a geometric explanation of the toposes obtained from triposes via the tripos-to-topos construction, because we are presenting these categories in terms of category of Presheaves and Lovir-Kearney topologies. All the results are contained, a part of these results is contained in this work, and the tool that we use to lift the adjunction between triposes to toposes is contained here in this work by John Spray, where he analyzed the two categorical properties of the tripos-to-topos construction, saying basically that every adjunction which is between triposes can be lifted to their toposes. And as application, as example, we have, of course, the ordinary case of the sheafification for localic toposes, because if we apply our construction to the localic tripos, we obtain here the category of Presheaves, here the category of Sheaves, and the sheafification. But we also obtain here in the setting of realizability triposes, let me say, geometric presentation of realizability triposes as realizability toposes in terms of sheaves for a certain Lovir-Kearney topology. And this is our main applications, and of course, as future work, we would like to extend our approach and find more connection with Grothendieck topologies and Grothendieck toposes. And here you can find a short list with the main references that I used during this presentation. So thank you very much for your attention.